Alright, so NASA just checked in on 3I Atlas again today, and I've got to tell you, what came back is not what anyone was hoping to see at this point. This interstellar comet should be ending at this point. It should be fading quietly as it returns to deep space. However, the data speaks for itself. It tells us a completely different story. 3I Atlas is still active. And not just a little bit active. We're talking genuinely, measurably, significantly active in ways that have scientists scratching their heads and recalculating their models over and over again. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. Now, if you've been following along with me on this journey, you know this comet has been absolutely wild from the beginning. But we're at a point now where things should be calming down. We're past peak. The comet has already made its closest approach to the sun and is heading back out. According to the textbook, this is when things get boring. The textbook is apparently wrong. So let me walk you through what today's check actually revealed. Because every single piece of information we are acquiring is pointing in the same direction. And that direction is becoming more and more worrying as the days pass. Let's start with the most basic measurement they take every single time they point a telescope at this thing. They're asking one simple question. Is it dimming the way it should be? Now, on paper, by every model we have, by every bit of physics we understand about comets, the answer should absolutely be yes by now. 3I Atlas is further away from the sun than it was when it hit peak brightness. The sunlight hitting it is weaker. There's less energy pumping into the surface. Standard comet behavior says that means less heating, which means less ice transforming into gas, resulting in less dust getting thrown off, which means the whole thing should be getting steadily fainter in a nice, predictable, smooth curve downward. Except that's not what's happening. Not even remotely. When the team overlaid the brightness measurements taken today on top of the expected curve, the real comet is running high. Like, noticeably high. Yes, it is less visible than it was at maximum brightness. That's true, but it's nowhere near as faint as it should be at this distance. The light curve isn't falling cleanly like it's supposed to. Instead, it's doing this weird thing, where it flattens out. It's like the comet is refusing to follow the script. What does that actually mean in plain English? It means this thing is still venting way more material than it has any business venting at this stage of the game. Now, you might think, okay, perhaps it's just dust that has remained hanging around, still reflecting sunlight, making it look brighter than it actually is. That's a reasonable thought. If that were the case, though, you'd expect the inner glow around the nucleus to look tired, washed out, diffuse, kind of like how smoke looks hours after a fire has been put out. But when they stack the newest images from today's observations, that is unquestionably not what they saw. The Comet, that cloud of gas and dust surrounding the nucleus, is still structured. And I mean really structured. Right around the nucleus itself, you can see this bright inner region with a really sharp gradient, like a tight ball of light that suddenly fades as you move outward. And wrapped around that, there are these faint arcs, these ripples, that almost look frozen in space. Some of those shells match up with older outbursts we've already documented. We know where those came from. But here's the thing. One of them is new. There's a tighter, fresher ring in the most recent photographs that was absent in earlier stacks. That ring is telling us something really important. It's telling us there has been at least one recent release of brand new material late in the game, at a time when this comet should absolutely be calming down and going quiet. And then there's the tail. You'd think by now, the tail would have sunk into a diffuse, soft smear, right? Just old dust, gently drifting away, spreading out, losing definition. But no, the spine is still there. There's a bright, narrow line of dust running straight down the center of the tail, with fainter material fanning out the other way. As spine structure only occurs when there is an active, focused stream of material being fed into it. It's not a relic. It's current, belt. So just from the visual data alone, today's check is screaming the same message as the brightness numbers. This is not a dead object coasting through space. This is not something that's done. This thing continues to function still, throwing off material, still doing stuff. But wait, there's more. And honestly, this section may be even more telling. They also measure the rotation of 3I Atlas with every check-in. How do they do that? They watch how the brightness changes over hours as the nucleus spins. If you have a basic, quiet, inactive nucleus just tumbling through space, you get a simple, repeating pattern in the brightness. The peaks arrive promptly, like clockwork. The shape of the curve stays consistent. It's predictable. Today's light curve didn't do that when they took the newest photometry data and tried to fold it. Over the rotation period they'd calculated from last week's observations, the peaks didn't line up. The main brightness peak is showing up a little bit earlier than it should. And there's this secondary bump in the curve that used to be small and barely observable. Now it's taller, more distinct, and more prominent. To get all the data to match up properly, they had to adjust the rotation period again. They had to shave a little bit more time off each complete rotation each day of the comet, if you want to think of it that way. The comet is still spinning up. Its rotation continues to accelerate, and that secondary bump that's gotten stronger and more stable with each rotation. That's basically the comet announcing to us, hey, there's a second active region on my surface and it's not shutting down anytime soon. So let's take stock of what we've learned from just this one routine check-in. We've got 3 major red flags waving right in our faces. Number 1, the overall brightness is significantly higher than what the models predicted it ought to be at this distance. Number 2, a brand new shell is emerging from the inner coma, evidence of an obviously recent outburst, something that just happened. Number 3, the rotation signature is telling us that not only are there still active vents, there are multiple vents in there, not just firing randomly. They're gaining influence. They're becoming more prominent in the data. Now, if that wasn't enough, let's talk about the thing NASA cares about most when it comes to tracking this object's trajectory: non-gravitational acceleration. Every time they get fresh position measurements of where 3I Atlas actually is in space, they rerun all the orbital calculations. They're asking, how much extra acceleration beyond the sun's gravity do we need to add to our models to match where this thing really ended up? When you have active jets shooting gas and dust off the surface, those jets act like tiny rocket engines. They push the comet. They change its path in ways that gravity alone can't account for. If 3I Atlas were finally settling down and going quiet, those non-gravitational terms in the equations would be getting smaller and smaller, trending toward zero. The comet would start moving more and more like a simple, quiet rock ruled almost entirely by the sun's gravitational pull. Today's updated orbital solution doesn't show that at all. The non-gravitational acceleration is still there. It's not spiking the way it did at peak activity, sure, but it's also not fading away in the clean, smooth, predictable way you'd expect if things were really winding down. To make the math work, to make the predicted position match the observed position, they still need to include a steady little push coming from those dust and gas jets. So let's review. The brightness data says it's still active. The structure of the coma says it's still active. The rotation behavior says it's still active. The orbital dynamics say it's still active. Every single piece of evidence from today's NASA check is pointing to the same conclusion. 3I Atlas remains active. There's no ambiguity here. The data is clear. But here's the thing, the most important question is no longer whether it's active. Today's data answers that beyond any doubt. The real question now is why it's still active and, more importantly, how long this can possibly continue. To understand that, we have to start thinking about what's going on inside the nucleus itself. And as soon as you do that, this whole situation starts to make uncomfortable sense. The close proximity to the sun did more than just warm the surface and then leave everything alone. It started a process, a slow, deep, ongoing process that's still playing out right now. Think about it this way. The outer layers of the comets heated up first. All of the initial drama took place there. That's where the activity came from, the big jets, the bizarre shapes in the coma, the sudden flashes and flares we saw. All of that was the surface responding to the sun's heat. However, heat extends beyond the surface. Heat spreads. It conducts inward slowly but surely, penetrating more and more deeply into the comet's interior. And here's the critical thing. The comet's interior is not uniform. It's not just a solid ball of ice. It has pockets and veins, old fracture planes, and cavities, all filled with different types of ice saws that have been locked away. Frozen solid, virtually unaffected, for billions of years. These ASAs have not experienced heat since this comet formed in some distant stellar system we can barely imagine. Those deeper pockets don't care that the comet is technically outbound. Now they don't care that we're past perihelion. All they care about is one thing. Has enough heat finally reached them? Have they finally gotten warm enough that the ice can begin to sublimate directly from solid into gas? If the answer is yes, they vent. As easy as that. And every single time one of those hidden reservoirs wakes up, 3 things happen simultaneously, and they're all bad news for the structural integrity of this object. First, gas and dust rush out into the coma. That creates a fresh shell, a new bright region, a spike in the brightness measurements. That's what we're seeing in today's data. Second, the direction and strength of the jets change. When a new vent opens up or an existing one changes, it's output that changes the balance of forces acting on the nucleus. It nudges the whole thing. It tweaks the spin. It's literally pushing the comet in ways that weren't happening before. The third element is the one that really worries people. The comet's internal stress map organizes itself. When gas builds up pressure and then suddenly releases, it affects more than just the surface. Cracks open up in the interior, old faults, old weaknesses in the structure. They widen. New pathways to the surface appear. The entire interior structure of the comet gets scrambled. From the outside, looking at it through our telescopes, all of this just looks like it's still active. However, from the interior's perspective, from a comet's perspective, layer by layer, is being forced to respond to a star it only encountered once. It's an ongoing crisis that started at perihelion and hasn't stopped. And that's exactly why today's check-in matters so much. Why this isn't just an interesting data point. Why scientists are watching this so carefully. A comet that continues to be this active so far from the sun isn't just a fascinating light curve to study. It's a stressed object. It's an object under strain. The longer it keeps venting this hard, the more torque those jets exert on the nucleus. The more its spin continues to evolve, and the more mechanical load gets placed on a structure that we already know is riddled with weaknesses, faults, and cracks. This has been seen before with other comets in our own solar system, the ones that keep staying active late in their orbit, the ones with changing rotation rates and complex structures that maintain throwing off fresh material. Those are the ones that flirt with disaster. Some of them pull through. They hold together. They eventually quiet down and drift off, intact, into space. Others don't make it. They fragment, they split, they fall apart. Right now, as of today, 3-2 Atlas is still officially classified as a single nucleus. There's no confirmed split. There's no clean secondary object visible. There's no obvious debris trailing out behind it. But those status labels, those classifications, they don't actually change the underlying physics of what's happening. The most recent data is crystal clear. This thing is still spinning, even if only slightly. It is still releasing fresh material with each rotation. It remains pushing against its own orbit with non-gravitational forces. The question we should be asking isn't, is it active? That's been answered definitively. The real question, the one that matters, is how long can it possibly stay this active without something giving way? Consider what is taking place here. Every rotation, the nucleus is experiencing torque from asymmetric jets. Every outburst is releasing pressure from the interior in ways that stress the material. Every time a new vent opens, it's weakening the structural integrity just a little bit more. This is not sustainable indefinitely. Something has to eventually give. If tomorrow's observations show the same level of activity, the same non-gravitational acceleration, the same fresh structures appearing in the coma, then we'll know the current phase is far from over. We'll know that 3I Atlas is continuing to push whatever limits a comet nucleus can withstand. On the other hand, if we finally start to see the light curve beginning to slide downward in a meaningful way, if those shells stop forming, if the non-gravitational push begins to drop consistently, then maybe, just maybe, this is the beginning of the end. Maybe this will turn out to be the last chapter of what has been an incredibly loud, incredibly violent, extremely stressful meeting between an interstellar visitor and our sun. But either way, these daily checks that NASA's doing aren't just routine box-ticking exercises. They're not simply collecting data for an academic paper that'll come out in a few years. These observations are functioning like a heartbeat monitor on a patient in critical condition. They're tracking the vital signs of an interstellar comet in the middle of its one and only shot through our solar system. Right now, that heartbeat is not slowing down the way it ought to be. Every day we check, we're learning whether that heartbeat is finally starting to stabilize, or whether it's going to stay elevated right up until something dramatic happens. And when I say dramatic, one mean breakup, fragmentation, a division, that transforms one item into two or more. That's what's on the table here. That's the possibility that every new data point is either moving us toward or away from. This is why I keep coming back to this story. This is why today's check matters. This is why tomorrow's check will matter. We are watching, in real time, an object that traveled here from another star system. Object that's been traversing the void for who knows how long, potentially millions of years, and it's now in the process of determining whether it survives. It's meeting with our sun. The fact that it's still this active, this far out, this long after perihelion, tells us it's on the edge. The physics is clear, the data is clear, the stress is real and ongoing. Therefore, when NASA published today's check-in data and I saw that everything was still pointing towards sustained activity, my first thought wasn't, oh, cool, data. It was, this thing is still in trouble. And we're going to keep watching. We're going to keep checking, because this story isn't over, not by a long shot.